So, welcome back for the fourth lecture of this week. So, we had already started our discussions on word sense disambiguation in the last lecture, and we talked about some approaches that that are either knowledge based or use some machine learning algorithm. So, in this lecture we will talk about some approaches that are either semi supervised or unsupervised. So, why do we need to talk about the semi supervised or unsupervised approaches? So, in all the machine learning approaches that we can use for this particular problem or any other problem, what is one particular bottleneck? So, let us take the Naive algorithm. Okay. So, for applying Naive algorithm, you want to compute the feature set, that is as such easy, some sort of domain knowledge will be required, but you have to find out all these numbers, like what is the probability of a particular sense, what is the probability of a feature given a sense. Yes. Now, how do you get all these values? For getting all these values, you need to have some sort of label data set. And what do I mean by label data set in this context? I will have various sentences where this my ambiguous word would have occurred, and somebody has labeled it that this is sense 1. In this sentence the word W occurs, this is sense 2, and so on. So, in a good number of sentences somebody has labeled each word as belonging to one or the other senses, and from there I can compute all these scores, and this has to be done for each and individual word. Okay. And this can be really expensive, getting all these annotations done, and that is true for any generic machine learning task. So, you need to have all these annotations first, and that is quite expensive. That is why if you can find some sort of semi supervised approach where starting with very few labels you can generate lot of different labels, and which may not be 100% accurate, but you can assume that they are mostly correct. So, that is also quite well appreciated, that is you are trying to use some sort of semi supervised approach, and that will save a lot of efforts in labeling, and also you use a lot of bootstrapping here. So, you see one such approach for word sense disambiguation that was proposed by Jarowski. So, this is also called minimally supervised word sense disambiguation. And what is the motivation? That for using a supervised learning algorithm I have to use annotations, and that is quite expensive. So, I use bootstrapping. So, what is the idea? I start with some small seed set, and I am learning my decision list classifier. From the small seed set, use my decision list to label rest of the corpus. Again from there find out what are the labels that are confident, modify your decision list algorithm, again run it on the corpus, find out more labels, and so on. So, you try to go in some sort of a loop of starting from some seed set, labeling some sentences, extending your seed sets or patterns or rules, again applying it, getting more labels done, and so on, until you are somehow converging. So, and you can use some sort of heuristics for doing this semi automated labeling, and two heuristics are very common in the case of word sense disambiguation. One is one sense per discourse, and another is one sense for collocation. One sense for collocation we have already seen in the previous example of decision list classifier. What is one sense for discourse? So, idea is that suppose you are taking one particular document or one particular long context. If the same word has been repeated multiple times, most probably it is used in the same sense. So, for example, you are seeing a cricket commentary or some news article about sports, and you find that the word bat has been used at one point, and you know this category is sense 1. Now, if the same word bat occurs in some nearby places, you can probably assume that this is also being used in the same sense, and this is the idea. So, in the same discourse, if a word occurs multiple times, I tag it with the same sense. So, these are my two different heuristics, one sense per discourse, that is a word tends to preserve its meaning across all its occurrences in a given discourse. And one sense for collocation, we have already seen that if it is used with the same collocation, it will have one meaning. And generally it is strong for nearby collocations, and if the distance becomes higher, it becomes weaker and weaker. So now how do we use these ideas to construct a semi-supervised approach for word sense disambiguation? So idea would be, let's take the same example, that is, I am having the word plant. It has two senses, one is industrial sense, another is living thing sense. So I will start with some sort of seed labels or some seed collocations. So suppose I say that with the first sense, that is industrial. If the word plant occurs with manufacturing, it will have only the first sense. Similarly, if the word plant occurs with life, it will have the living thing sense. Okay. So this becomes my decision list classifier. I check simply if the word plant is occurring with manufacturing or life. Manufacturing, I say it is sense 1, if life, sense 2. Okay. So what will I do? I will take my whole corpus. See, wherever with the word plant, one of these words, either manufacturing or life, occurs. Wherever the word manufacturing occurs, I will say, okay, this is labeled as, this is my pseudo labeled sentence. So now I have some set of pseudo labeled sentences, both with manufacturing and using manufacturing and life. So what I would have now, from my corpus, I would have labeled some sentences, okay, with sense 1, with sense 2. So these are all the sentences where the word plant occurs with manufacturing, and these are all the sentences where the word plant occurs with life. Okay. So now the idea would be, so now I am going in iterations. So now I will treat them as my labeled data. Okay. Although to be very clear, we can also call it my pseudo labeled data. It is like I am only making an assumption that they are labeled with sense 1 and sense 2. Now treat it as your labeled data and then apply your decision list classifier algorithm to find out what are the good collocations. Suppose you find some 3-4 collocations here. So it can be different things about growth and whatever, or the word car, like what we saw in the previous case. So you find some collocations here. Now use these collocations and your algorithm to build a new decision list classifier. New classifier. Again you will use that to label new sentences, and you will have new data, you will get new collocations from there, and you keep on repeating this step. So let us see for this particular example. So suppose I use that and I label some sentences with sense of living thing, some with sense of industrial plant. Okay. So you see here everywhere life is occurring, here everywhere the word manufacturing is occurring. Now from these labeled or my pseudo labeled data, I will try to extract some more collocations. Like here, suppose I see that the word like animal and kingdom occur a lot with this sense, but they do not occur with this sense. So this becomes my collocation now. Now use your decision list classifier algorithm previously that we have talked about to make make my decision list. Okay. Now again run it over the corpus, and there you can find, suppose, the words where plant and animal occurs. So here you can again label it with sense of living thing, and from once you have done that, you can extract some more collocations from here, and you keep on doing that. So the idea would be something like that. So you have this whole corpus where the word plant occurs. Somewhere by using this initial seed set of life and manufacturing, you have labeled sense A and sense B. Now what you will do, you will treat them as labeled data, from there capture some more collocations. So something like this. So you capture collocations like cell, animal, species, microscopic for the sense of life, and equipment, employee, automate and manufacturing for the sense of industrial plant. Now use that to label more sentences. and this is the more sentences that you have labeled. Okay. So, all these content this microscopic, species, animal, and so on. Now, you have a larger data, again extract collocations from here, build your decision tree and try to label the rest of the corpus. So, you keep on iterating this, and ideally at some point you will have your whole corpus covered. Now, so when do you stop? When the error on the trained data is less than a threshold. So, you can have some small trained data to check how good your this bootstrapping approach is performing, or when no more trained data is covered by the algorithm, when you see that all the examples have been covered, and when whatever final decision list you get by this algorithm, use that for word sense disambiguation. Now, what is the advantage of this approach? So, so you can see the advantage here are that you do not have to put the efforts into manual labeling of the corpus. So, you can start with some very small seed sets, keep on applying this algorithm iteratively and obtain your final classifier. Now, so accuracy also turns out to be quite good, but what are the different what may be one problem with this approach? So, one problem with this approach might be that the whole accuracy that you get by this approach depends on how good are your initial seed set. If your initial seed set is not good, then you may not go very far in this approach. So, the good thing is if you choose very good initial seeds that have lot of representation in the corpus and are also very distinctive. Okay, so, this starts giving you very good precision and good recall from the very beginning. So, now this is a semi-supervised approach, and I hope the idea is clear. Now, we will see one unsupervised approach for word sense disambiguation. So, by unsupervised I would mean that the senses for the words are not defined a priori, but they are sort of learned from the data. So, from the data you try to find out what are the different senses a word is used in, and this becomes your sense definition for each word, and this field is also called word sense induction as such. So, you are trying to induce the senses of the word by its usage in the corpus. Now, what is the basic idea? So, we will talk about the algorithm hyperlex. So, key idea here is word sense induction, that is, instead of taking some senses that are defined by a dictionary, try to extract the senses from a corpus itself. So, the way the word is used in a corpus, use that for extracting senses of the word, and these corpus senses or usage will correspond to clusters of similar contexts for a word. Now, let us take one example to get the intuition. So, here you are seeing the word space, and there are many other words that are coming along with this space. So, the connections show here that two different words occur together in a above some threshold number of times in a corpus. Okay. So, an edge denotes that they are probably similar in the sense that they are co-occurring a lot. So, now try to look at this picture. So, what you are seeing, the words like retail, parking are connected, retail square are connected, feet and parking are connected here in the left hand side. Right hand side you are seeing words like astronauts, mission, and NASA, shuttle, all these are connected. Now, by looking at these connections, so what is one thing that you are seeing is that you are finding out two different clusters here, okay, one in the left hand side, one in the right hand side. One is denoting one sense of space in the sense of parking space, retail space, and second is space as such, space where astronauts will be going in, and that involves NASA and all that. Now, from the corpus I can find out that astronauts, NASA, and shuttle NASA are connected, retail, parking, retail square, all these are connected. But how will I find out that the word space has two senses and these two senses correspond to some particular words? So, if you look at the figure again, you can see that for a particular sense of the word space, the words will be highly connected to each other. For another sense again, these words are highly connected to each other. But there will not be much connections between the words in this sense and words in that sense. So that is, if I construct this as a graph and can use some sort of clustering algorithm to find out what are the different portions or partitions of this graph. So one partition will belong to one sense, another partition will correspond to another sense. And this is the idea. Try to exploit how much for the same sense, the words will co-occur a lot together, but it will not happen for the words across two senses. And there are many different algorithms that are developed based on this idea for word sense induction. Okay. So now we will talk about a very simple approach, hyperlex, that uses this idea. Now what is this algorithm hyperlex? So what it does is that for a given word that is ambiguous, by using the data in my corpus, it tries to identify what are the main hubs. So each hub will correspond to one sense of this word. So it tries to identify what are the main hubs, and every other word in my co-occurrence graph will be connected to one or the other hubs. Okay. So you know everything is divided into these hubs. So how do you detect these hubs and how do you connect the words to one of these hubs? So in hyperlex algorithm, the idea is that the different usage of the target words form highly interconnected bundles or high density components, and each component will have one of the nodes. This is hub that is having a high degree than the other nodes. So how do you start applying this algorithm? So firstly you have to construct your co-occurrence graph. Co-occurrence graph we have seen already in the previous week, that I will find out how many times these two words occur in the corpus, and I use some function of that to find out how much their association is strong, how strong is their association, and I will probably retain only those words that have a very high association. So I start by building this graph from the corpus co-occurrences. Now, so what do you do? This graph is connected around this word, this ambiguous word, like a space in the previous example. So first thing I will do, I will arrange all the nodes in this graph in the decreasing order of their degree. So I will forget about the word space, but every other word will be connected in the decreasing order of their degree. So what I will assume that whatever the hubs are will have high degrees here. So take the node that is having the highest degree among all the connections, and this will be the first hub. Try to find out what is the neighborhood of this hub. Take them to this sense cluster. Remove this from the graph altogether. From the remaining graph, find out what is the node with the highest degree, make it the second hub. Find out its neighborhood, make it the second sense cluster, remove it. Keep on doing that. So once I have arranged the nodes in graph G in decreasing order of degree, now select the node from G that has the highest degree, and this will be the hub of the first high density component. Now delete this hub and all its neighbor from the graph. From the remaining graph, again repeat the step 3 and 4 to find out what are the hubs and what are their high density components. So let us try to see this algorithm on a simple example. So here what do you have? You have the word bar, that is the central word, and I want to detect what are its different senses. So what we have done, we have first tried to construct the co-occurrence graph. So this is what you are seeing is a co-occurrence graph that tells what is the strength of association between two words. Okay. One thing here, so I will talk about what is the association measure. So according to this association measure, you will take a threshold and choose only those edges that are above or below the threshold, depending on how you are defining your threshold. In this particular case, so the number denotes what is the distance between two words. So you are only retaining those words whose distance is below a threshold. Say your threshold is 0.25, so we will retain only those connections that are below 0.25. And distance can be captured by something that is inversely proportional to the association. So, in this case it is 1 minus probability of max of probability. So, it is 1 minus max of probability Wi given Wj and probability Wj given Wi. So, we take the max of that to find out what is the association between Wi Wj, and this will now capture the distance, because this corresponds to the similarity, how similar they are, their conditional probability. If I take 1 minus max of that, that is how much they are different, what is their distance. So, once we have done that, for all the words, all the pair of words, I will take only those that are having distance below a threshold. That means they are quite near, and that is captured in the left hand side of the figure. Now, once you have done that, now you apply your algorithm, that is finding out what are different hubs and taking their different neighborhoods. So, first I will arrange all the words in decreasing order of their degree. Now, what are the nodes here that are having the highest degree? So, you find the word like iron. Iron has a degree of 1, 2, 3 and 4. Coffee has a degree of 1, 2, 3 and 4. Wine also has a degree of 1, 2, 3 and 4. Okay. So, now there are multiple words that are having the highest degree. So, we will choose some preference, maybe either in the lexicographical order or some ordering on the, or some traversal ordering on the graph. And suppose you say from, I will choose the one from the left, and you choose the word like iron here as your first hub. So, what is next step? Make iron as your first hub, and then take all the neighbors of iron and put them with this hub. So, you are taking the two neighbors, gold and steel, and putting them with this hub here. Okay. And that becomes your first hub and its components. Now, how do you find the next hub? You remove this hub and all its neighbors. So, I remove iron, gold and steel from the graph. Again, find out what is the node with the highest degree. You will find the word like coffee here. So, take coffee as the second hub, take its neighbors. So, it will be chocolate, cocktail and wine. So, these become its neighbors. This become my second hub and all the component with that. Remove that from the graph. Now, find out the next hub. So, this can be the word soap, that is having a degree 3. You take the word soap and wax as your third hub and its component. And then finally, you will have the word like pressure and dyne, that is your 4th hub. So, this is my hub and these are different descendants of the hub. So, from your corpus, you are focusing on one word here bar, and you are trying to construct the co-occurrence matrix, finding out the association between various words, building out this graph. From there, you are detecting what are your various hubs and their descendants, and this becomes your structure now. This is your target word, different hubs and their descendants, and this is what you have obtained in a completely unsupervised manner, because nobody told you how many senses the word bar would have, or what are the different senses of bar. You found it automatically by using the corpus data. So, for all other words other than hub, you attach them to the root hub that is closest to them. And how do you find what is the closest hub? You can take the distance between that node and the different root hubs. Okay. And this distance is simply the summation over the path length. What is the path length? You just keep on adding the path length. That is the distance between any node and the root hubs. Attach each node to one of the root hubs only. And this is something that I talked about, that how do we compute the distance between two nodes in my original co-occurrence graph. I take this 1 minus max, probability of Wi given Wj and probability of Wj given Wi. So, now, so we can see that how do we start from my corpus and construct different senses of a word, so by hub and descendants. Now, at runtime, so we are talking about this problem of words in disambiguation. So, at runtime, I am given a sentence where this word is provided, and I want to find out what is its appropriate sense that is used. among all the possible senses I have found by this algorithm. So, what is the approach? So, let us say I have this context or the sentence where this word wi occurs, and wi is my target word that has multiple sensage. So, suppose it has k sensage, k hubs, that is k sensage. So, what do? We associate a score vector S with each word in the context such that Sk denotes what is the contribution of the so what is the contribution it will have to the kth hub, and this is simply taken by 1 divided by 1 plus distance between the hub and the word. If the hub is an ancestor of the word w, otherwise it is 0, and you do that for all the words in my context and sum those over. So, you find out a simple vector that tells me which sense has how much score, which hub has how much score, and whichever hub has the highest score, I will choose that. So, to tell that again, so what we will do? So, we will have a sentence w1 to wn, and I have this word wi that has s1 to sk, k hubs. Okay. Now, I want to find out which of these k senses is used in this particular example, a particular sentence. So, what will I do? For each word w1, w2 up to wn, I will construct a score vector. Okay. So, a score vector has that many dimensions as the number of hubs. So, it has k dimension. So, I will construct this vector for each of the words. Okay. So, now what are the entries in this vector? So, this entry tells me how much contribution this word will make to the first hub, and this contribution would be, if this word is an ancestor, if the particular hub h1 or the sense 1 is an ancestor of this word w1, it will be 1 divided by 1 plus distance of h1 and w1. Okay. So, that is, if the distance is high, this score will be low. If the distance is smaller, this will give a high score. On the other hand, if this word, if the hub is not an ancestor, I will put a score of 0. So, like that I will put all the different values here, and finally, once I have all the values, I will add all these. So, for each hub, I will add all the possible scores, and I will take a final vector, that is how much contributions all the words together are making for hub 1, hub 2 and hub k, and I take the one that is having the maximum score among all these, and that becomes my winner sense. Okay. So, so this is the overall idea of this approach. So, what we have done here, we did not start with any dictionary defined sense. We used a corpus and defined our own senses by seeing what are the different components that occur together. So, idea is that for a given sense of a word, different words would have a high co-occurrence. They will make some sort of cluster. So, identify different clusters as different sensage. Now, once you have these sensage, if you want to use them for word sense disambiguation at runtime, whenever the word is used, find out from the context words which of the different hubs they are closer to. So, whichever hub gets the highest score becomes your disambiguated sense. So, that's so these are some different ideas for approaching this problem of word sense disambiguation. Although, as I said earlier, there are many different approaches that have been proposed. So, in the next lecture, we will briefly talk about an idea of word sense discovery, that is, how do you find out if a word has got a new sense in the corpus. So, this is a relatively new field, and we will see how the ideas that we have developed in these lectures to use, how do we use them to find out if a word has got new sense in the corpus. Okay.